Okay, so let's look at a typical forces, work, and energy type situation and see what we can solve for. Here we got a guy with a 45 kilogram wheelbarrow going up a ramp that is 3.6 meters long. He's going to just start at rest at the bottom, and he reaches 1.2 meters per second at the top, and we've got him listed as having done 550 joules in order to go from the bottom to the top of the ramp. And what we're going to do is we're going to see if we can find out what the angle of the ramp is. Now you could probably use basic dynamics with your your forces, your FGX, and your speeds, accelerations, all that kind of stuff. But we're going to try and use work and energy in order to solve this. So let's go back to our basic expressions. First of all, we've got our work expression, and basically if you apply a force over a distance, you've done work. And they have to be parallel, and that's why you often see a cos theta at the end, because only the parallel force to the actual distance or displacement actually counts. We've also got gravitational potential energy, which is mgh, which is basically how much work you've done going against gravity. So it's actually the force of gravity times a vertical distance. So it's just a modification of this expression. And of course, we've also got the kinetic energy, the 1/2 mv squared. That is derived out of the kinematics expression. And we've done that derivation in class, but it's derived out of there. Okay, so we'll just see if we can use these expressions to figure out how things sort of can work together. Okay, so let's just start by finding energies and piecing things together, and we'll see what we can do. So first of all, if we just sort of look at what he actually did, of course he did work, which would be force times distance. And we can't find the force, we can't find the distance. Okay, so we're going to look at a really classic work and energy type scenario with a guy pushing a wheelbarrow up a ramp. It's a 45 kilogram wheelbarrow, 3.6 meter long ramp, starts at rest at the bottom, reaches 1.2 meters per second at the top, and he does 550 joules. So we're going to see if we can find a couple things. We're going to see if we can find out how much force he's actually using, and we'll get to be his applied force, and we're going to see if we can find the angle of the ramp. Now, if we just go back to our basic work and energy type expressions, we had work is equal to FD cos theta. So as long as you apply a force and it moves a distance or displacement, you have done work. And they have to be parallel to each other, and that's where the cos theta can kick in. That's just the angle between the applied force and the displacement. In this case, they would be nice and parallel to each other anyway. We've also got our gravitational potential energy is equal to mgh, which is just a modification of this one. That's just applying a force equal to the force of gravity over a vertical distance. So it's just this guy modified, and that's how much potential energy the wheelbarrow would have. It has 0 at the bottom, but it would have potential energy at the top, because basically if you can fall, you've got potential energy. We've also got kinetic energy, 1/2 mv squared, which we derived out of this expression, incorporating mass into it, and then we actually worked into the FD expression, and we got that one. We did that one in class. But as long as you're moving, you've got kinetic energy. So there's our basic expression. So let's see if we can apply some of this stuff to the situation. Now, to find the applied force, it's not actually that difficult. We know how much work he did. He did 550 joules of work, and we know how far he went. So it's actually a pretty straightforward calculation for that one. So the applied force would just be the work that he did divided by the distance it traveled. So that would just be the 550, and divide that by the 3.6 meters that actually traveled. And he did, we'll round off here, he did about 153 newtons of force. So that's how much force he's actually applying to the wheelbarrow. Okay, so now let's see if we can find the angle involved. Now, there's a couple ways we can actually do this. We could incorporate FGX, MG, sine theta into the situation, that kind of stuff, but we'll try and do just work and energy type stuff. So what we're going to do is we're going to try and use distances. We have the speed at the top here, so I can actually find the kinetic energy at the top. So if I find the kinetic energy at the top, if I find my kinetic energy, 1/2 mv squared, I've got my 1/2 obviously, I've got my mass of 45, and then I've got a speed of 1.2. Don't forget to square it. And my kinetic energy at the top is around 32 joules. So he did 550 joules of work altogether, and 32 of that went towards kinetic energy. So if he's got 550 done in total, 32 of that went to kinetic energy, that tells me that the potential energy at the top has to be the difference. So that'd be 518 joules of potential energy. Because whatever work he did, that went to two things. Number one, lifting it, as well as moving it and having speed at the top. So the total energy of these two put together have to add together to give me my 550. Well, now that I know how much potential energy it has, I can use my MGH expression to solve for the actual height of the ramp. And let's see, that'll give me about 1.17 meters. And remember, it doesn't make any, in terms of potential energy, it doesn't matter if he lifted it straight up or went up the ramp. The potential energy at the top is the potential energy at the top, no matter how he got there. So now I actually have the height of the ramp, and it's just a triangle. So if I sort of piece things together, I've got the ramp going this way, which is 3.6 meters. I found out that the height is 1.17 meters. It's just a right triangle, so now I can use trig in order to actually find out the angle. So I would just use my sine function. Sine is just opposite over hypotenuse. I can use the sine function in order to solve for my angle. And that would give me an approximate angle of around 19 degrees. So there you go. The angle is 19, the force applied is 153. Now this is one way to do it. There's a few ways it could actually be done, but this is just doing the solution, practicing using our work and energy equations and situations. Okay, so I just shrunk down all the work that we did and sort of moved it over here a little bit because we're going to adjust the situation a little bit and see what else we can do. So what if we change the situation? Maybe we incorporated some friction and stuff like that, maybe some friction in the wheel or something like that. There's no sliding friction, but what if we incorporated some friction? So maybe he's just only going 1 meter per second at the top, and we wanted to find out what is the force of friction. Okay, well, this is not exactly the hardest thing to do. Again, we could crack out some old kinematics and dynamics to figure it out, but we can also use some of the energy type stuff. So if I'm only going slower, that means I've actually changed the kinetic energy. Before, my kinetic energy was 32 joules. So I had 32 joules of kinetic energy. Now my kinetic energy is going to be less because I am going slower. So if I do the same type of calculation, new kinetic energy, 1/2 mv squared, I can calculate that my kinetic energy at the top from a slower speed is going to be about 22.5 joules. Okay, so he's still done 550 joules of work. He still has, or the wheelbarrow still has, 518 joules of potential energy. The only thing is some of the kinetic energy that I had before, some of that 32 has now been lost to friction. So if I sort of just summarize a little bit, in the previous question or the previous setup, he did the work. And the work went to potential energy and the work went to kinetic energy. Now we've changed the situation a little bit. He still has done work, still has gone to potential energy, still has gone to kinetic energy. This one has not changed at all, but the kinetic energy got smaller because some of it is actually going to the force of friction. So instead of being split 2 ways, now it's being split 3 ways. But the potential energies are the same. It's still the exact same height. We've just made that kinetic energy a little bit smaller, and some of that energy went to friction. So before, I had 32 joules of kinetic energy. Now I've only got 22.5 joules of kinetic energy. So we've lost, just subtract the 2, we've lost 9.5 joules to the force of friction, and this would be the work that friction has done. So it's not very much. Well, now that I know the work that friction has done, the 9.5 joules, I can find the force of friction just by doing work equals Fd. I can take the work that friction has done and just divide it by the distance that friction acted on, which is just the 3.6 meters, and I can actually find out the force of friction. So I just take that 9.5 joules and divide it by the 3.6, and that's probably around 2.5 or so, and we're looking around 2.6 newtons for the force of friction. So this is a way to find an overall force of friction without needing a coefficient of friction, no sliding friction, just a little different way to do it, just by using work and energy expressions. So again, similar questions that you've done in kinematics and dynamics, the fundamental type stuff, just a different viewpoint, different aspect using work and energy.